Swayam Prabha. Digital India. Educated India.
Let me introduce the first speaker, Professor David Shan Wang. There have been 3 waves of artificial intelligence, as most agree. The first one started at around 1990s, where perceptron was devised, and this can be, which mimic the operation of a cell, and it can be used for discrimination. Okay? But after some hype, the enthusiasms have died until 1990, where a second wave of artificial intelligence emerges, and this wave have 2 main branches. One is the expert system, which is a collection of rules from experts, and the resolution of them using fuzzy logic. But there is another branch which is called the artificial neural network, which is a collection of the perceptrons, and we can prove that this artificial neural network is actually a universal function approximator. Okay, it can approximate any continuous function and therefore can be used as models. However, this wave also dies for a while because there is no reason that the artificial neural network can approximate real functions with limited data. It cannot extrapolate or interpolate even there's a large data gap. And also during this phase, you can see that languages or and numbers are treated in different ways. We are in the current wave, which is called the deep learning wave, the deep learning wave enables functionalizing between different types of data, rather be it numerical, categorical, or text-based, audio-based, graph-based, image-based, whatever. So actually, we are in a phase where we can build a model or functions between different types of data and with no distinctions between them. So in the second way, we can approximate any functions, and in this way, we can functionalize everything. That is the key for this development. However, there are 2 problems still remain. Even with deep learning, it is still data-driven. Okay, there's no guarantee that the approximation is good when data are scarce. That's why we need big data to train our models, and there is also no guarantee that big data will cover everything. So there's a important desire to leverage known physics, because we have all learned a lot of things over the years about how a chemical process operate and how physics operate. So leveraging known physics and ensuring reasonable extrapolation is a desirable features in deep learning. The other thing is that as the capability of artificial neural network increases, we want to model more and more complex systems. I shall use a one-dimensional heat transfer problem as an example. In this problem, the system is represented by a partial differential equations, very simple partial differential equation with boundary conditions and initial condition. Also, we have an activation function, is how heat is supplied to the system at different position and different locations. So we call U an activation function. So the solution of this equation y as a function of t and z is not only a function of z and t, but also, there's a mistake here, is also a function of u and y0 of z. So instead of yz of t being a function, it is a functional because it is a function of a function and is an operator. So how do we approximate such a functional or an operator? Okay. In 2019, a very popular paper known as Physics-Informed Neural Network was published. They used a very simple concept that physics compliance can be incorporated into a neural network by introducing not only the prediction loss term, but a PDE loss term. So given a neural network, we can do partial differentiation with respect to t, with respect to z, and then we can force the different derivatives to obey the PDE. So we introduce a term called the PDE loss. And they can show that the PINN can be used to solve PDE or carry out system identifications for complex problems. However, in their original paper, they have a fixed boundary condition and initial conditions and has no activation functions. In a later paper by the same group, 2021, they found that in order to develop a functional an operator, they developed what is known as the deep O-net model. Because a functional is a function of a variable as well as a function, they found that by using the variable and the function as an input into a neural network doesn't work. Okay, usually doesn't work. So what they did was to separate the two input into what is known as a branch net, where the activation function is used along as an input. And this is called the branch net, and there is another neural network that output the variables, and the other neural network has X as an input, and also this is called the trunklet. They found that a function, an operator, or a functional can be well approximated in this form by a dot product between the output of the branch net and the trunklet. Okay, this is known as what is known as the deep O-net. But if you use deep O-net to solve your PDE, it's still very difficult to train this deep O-net. We'll see later. So the objective of our work is to examine how the numerical solutions of the PDE to examine why deep O-net work from the point of view of the numerical solution of PDE, and we propose a simpler form of the deep O-net. We'll demonstrate the efficiency of our approach by a simple application to the heat transfer problem. One trick that we usually use in numerical solution of a PDE is to use what is known as orthogonal polynomial approximation. We approximate the solution by an orthogonal polynomial, where the y of x is a series of orthogonal polynomials. These polynomials have the orthogonal properties that the integration between two of them over a certain domain has to be 0, but integration of the square of one of these polynomial has to be equal to 1. But if we assume that any function can be approximated by an orthogonal polynomial, its derivative must also be approximated by a set of another orthogonal polynomial. And we can relate the coefficients of the two orthogonal polynomials by certain linear relations. So if we can do that, a normal numerical methods of solving PDEs is to approximate the output, the function by initial condition plus a product of two orthogonal polynomials. And we can calculate whatever derivatives and assume that the partial differential equations can be represented by an equation where we use the derivative operators on the orthogonal polynomial and make it equal to the activation function. Okay. And then if we do the integral, we can show that the coefficients of the original polynomial will be a function of the coefficients for the activation functions. So D will be a generalized function of A and B, which are the approximations of orthogonal polynomial expansions of the activation function. So using this theory, we can assume that, okay, the original deep O net, okay, we have a branch net where we input the activation function and initial condition to obtain D, and we input T and Z into a trunk net of T and a Z to a trunk net of Z, and then we do the dot product and multiply them together to get whatever we want, the function we want. But in order to satisfy the initial condition, the grid of initial inputs and the activation input has to be transformed into a continuous function in order to satisfy the PDE loss. Because we want to calculate the PDE loss, we need a continuous function of U and the continuous initial function to make sure that this can be satisfied at any point. But you can see that there will be 5 networks to be trained in this deep O net, okay? And involve a lot of parameters and a lot of data. But if we have the orthonormal polynomial series, we can prove that we only have to train one of these networks. The rest, all the trunk net can be replaced by orthogonal projection and inverse orthogonal transform of the particular domain. If we have domain of 0 and 1, we can do it. If we have domain of 0 to infinity, we can do it. So all these trunk nets all these 5 trunk nets can be transformed, can be replaced by orthogonal polynomials, projection and inverse orthogonal transformation from the original space to the orthogonal polynomial space. So this left us only one net, which is the branch net of the system that to be trained. So using this approach, we can much simplify the training of the neural network. And this is the example we demonstrated with. We have the same heat transfer problem. We divide the domain space into grids, and we provide the initial condition and the activation functions at different grids. We use different sets of initial conditions and activation functions, 100, 200, and 500, to demonstrate that as the data increases, the coefficients will, the accuracy of the model will increase. And we'll test the training of the neural network by another 1,000 sets of initial conditions and activation functions. You can see that actually why is it not showing? Okay. So the middle column is the deep O net. Okay. The original deep O net. It involves a lot of number of weights, and the training time is varies from data to data. But even though the training time is very small and changes from each, all the result shows that the deep O net does not converge. Okay, it fails to describe our data. If we use our orthonormal transformation, we can see the number of parameters in our system is much reduced by over an order of magnitude, and the training time is reasonable. Okay, and we can even get very high degree of accuracy with only, say, 100 sets of data. As the number of sets of initial and activation function increases, there's almost 100% correlations between neural predictions and actual solutions by PDE. So this offers a new method for us to solve a PDE and then get the results in terms of a neural network. And we can use this model for, say, model predictive control or optimization and whatever we want to do with the model. And we can also use this for system identification. In system identification, in addition to obeying the PDE laws, will give the system a certain set of data, and will minimize the prediction loss, but treat the parameters in the ODE system as variables. So we are doing system identifications, but however, in this case, we have to worry about the weighting between the prediction loss and the PDE loss and the boundary loss. And the students has found that, okay, we need to optimize the value of gamma, which is the weighting of the value loss, in order to get good predictions of the parameters. Okay, in fact, in this particular case, the thermal diffusion is particularly difficult to estimate. The conduction parameter is very, the estimation of the conduction parameter is very good. Okay. So using this example, we can show that compliance with physics can be incorporated into deep learning by including a PDE loss. It's no different than a simple neural network training, except that we add the loss function, a loss term to the system. So neural network portals are no longer data-driven only. We can use physics to drive the learning of the model. Okay, and for a partial differential operator, we can use the deep O-net the form to help our training with a branch net and trunk net form. And the trunk we have shown that the trunk net is only domain dependence. It does not depend on the specific problem. It only depends on the domain of the spatial temporal problem that you are tackling with. So in this case, we can develop complex spatial temporal evolution models in the form of neural network to be used in process system engineering that requires fast solution, such as online optimization or other model predictive control. Thank you.
I just wanted to ask, what is the time complexity for the training the deep nets as compared to solving by traditional methods?
It's no comparison for complex problem. It's still much better to solve it by, say, the traditional numerical methods. But the problem is you don't have to solve it every time. Once you solve it, you get a neural network model that you can use that solution for different inputs, different initial conditions, without having to solve the problem again. Let's say, with a new set of initial condition, new set of activation function, in traditional method, you have to solve it. But in this approach, after you solve it for 50 times, you don't have to solve it anymore. You have a model that you can put in any other initial conditions or activation function and get the solution.
Thank you. We have to move on to the next paper, so you can discuss later. But that's thanks to Professor Wang again. Thank you.